Okay, so what we have here is a statement about every positive integers. So what the problem says is that for all, it says consider any 3 consecutive positive integers. So for all positive integers k plus 1, k plus 2, where k is positive integer, and then what we want to show is that the cube of the largest cannot be the sum of the other cubes. Okay, so yeah, so that would mean that for all k, k plus 1, yeah, for all k, the following statement is true. K cubed plus k plus 1 cubed cannot be k plus 2 cubed. Okay, since this is a statement about all integers, I think it would the best approach would be to do it with proof by contradiction. Okay, and then we just assume the opposite. Okay, assume that we have there exists k and z plus plus and z and positive integers such that k cubed plus k plus 1 cubed equals to k plus 2 cubed. Okay, I really don't want to deal with k plus 2 cubed, so I'm just going to rewrite k as q minus 1, and this will kind of save me some calculations. Okay, then, yeah, if this is the case, then q has to be strictly bigger than 1, so has to be greater than or equal to 2. And then if we rewrite this equation with q, we get q minus 1 cubed plus q cubed equals to q plus 1 cubed. And then if we simplify this, I think we get q cubed plus 3 minus 1q squared plus 3 minus 1 squared q plus minus 1 cubed plus q cubed equals to q cubed plus 3q squared plus 3q plus 1. And then here I think we can, yeah, this q cancels this other q, and then this 3q is cancelled by this 3q, and then this I think this simplifies to q cubed minus 6q squared, and yeah, and this should equal to 2. Okay, this is what we have. We can't really say anything here, but yeah, okay, so if q is odd, then q cubed is going to be odd, and then 6 times q cubed is going to be even, since we're multiplying it by an even number, and then we're getting 2, but we know that odd plus even is always odd, right? So, and that's not the case here, so q has to be an even number. So q is 2 times m for some m positive, yeah, for some positive integer m. And then I guess we can rewrite this equation as 2m cubed minus 6 2m squared equals to 2, and then simplifying this we get 8m cubed minus 24m squared equals to 2, and then this, if we divide by 2, we get 4m cubed minus 12m squared equals to 1. But this is an even number, and this is also an even number. But we are adding two even numbers, and we're getting an odd number, and that can't be true. So this is our contradiction. Okay, and then now I just rewrote what I just said earlier here. So this is like the formal proof, I guess. So well, yeah, first we just say we're doing it using proof by a contradiction, and then we say there exists k such that this is true. But then we say that if k is odd, k cubed is odd, so and 6k squared is even, and we know that even plus odd is odd, so k can't be odd, so k has to be 2m for positive m, and then when we plug in 2m, we get another equation, and then we simplify that equation and we get even plus even equals to odd number, but even numbers are closed. They form an abelian group under addition. So that's where the contradiction happens. And yeah, I think that concludes the proof.